Assalamu alaikum. In the previous week, we have already started with the physical properties of the soil, and we saw how these physical properties really determine a lot of things in our life, the agriculture, the engineering, and many different aspects. In today's lecture, however, you're gonna learn even more interesting things. You're gonna, for example, understand and answer the question that why, for example, some of the soils needs to be irrigated more frequently than others. You're gonna see what would happen to the soil and the life. I mean, the plants, the organisms, when we do some activities like convert the lands into roots, we compress it, we walk on it, we drive our cars on it, and even different things. So in today's lecture, we're gonna start with the particle density, then we're gonna go through the concept of soil bulk density, then we're gonna see the relationship between bulk density and pore spaces, then we're gonna talk about porosity, then the factors that affect the porosity, and at the end of the day, we're gonna summarize some of the physical properties for different types of soil, so you're gonna see what is going on there. So without further delay, let's start. Now, before diving into the details of today's lecture, let's have a moment of think. Now, look at the picture to the left corner, top left corner, and tell me, what do you see? Think about it for a while. All right, I think this is enough time for you to think. Well, basically, we can see from the picture that there is some areas where there are vegetation, like it's covered with grass, and there are some patches, some areas where there is no vegetation, and not only that, the water only bonds on that particular place. Now, why does these things happen? What is the cause of that things? And what is the relation between soil, water, vegetation, and those patchy and vegetated areas? Well, let's see the story. Well, basically this is a picture which have been taken from a savanna in Africa, and what you can see that most of the area is covered with grass. However, there was a truck which was driven through the field, and in that particular area where the truck was driven, you can see there is no vegetation, and it is clearly that the signature of the tires is already there. Now, what happens when this happened? Well, basically, when the truck was driven on the soil, it compacted the soil and also it removed the vegetation because of the continuous driving in that area. And because of this, water was bonded on that particular area. Now, I want you to remember from the previous lecture that vegetation can open up the soil, like create baths in the soil, and that allows water to go in to infiltrate. But what happens now, that as you see from the second picture, that with the compaction, or when the truck was driven on the field, it basically compacted the soil, pressing it and removing the vegetation, and by this you reduced further the water movement, as you can see from the arrows, comparing the normal soil and the compacted soil. And not only that, the damage can be really devastating and can affect many other soil functions. You would know these details after you finish the lecture. So let's begin. Now, one of the fundamental things that I want you to keep in mind, that when we think about soil, we would find that it basically consists of three different components. Soil, the solid particles, which are the particles, and then you have the organic matters, and finally, you have the pore spaces, which can be occupied by water entirely or filled with air, or it can be partially filled with air and water. Now, what if we want to quantify these three things? What can we do? Well, basically, you can quantify them in a mass based, by which you just weigh these components. Then the total mass of the soil will be basically the mass of the soil, ms, plus the mass of water, mw, plus the mass of air, and you would find that the mass of air is almost negligible, like it's almost zero. Now, if you want to do this in a volume basis, then it's the same concept. The total volume of the soil is basically the volume of the solids plus the volume of water and the volume of air. Now, we know how to do the mass, but how can we measure the volume of the soil? Well, basically, we would use the same concept. Now, if you want to measure the volume of water, what you would do? You would take a graduated cylinder that is graduated, indicated with the levels, and then you put the water there and you can do it. In soil, there are different techniques, but you can imagine the concept like this. So you would be able to quantify the mass and also the volume of the soil. Now, why these two concepts are very important here? You would know later on because we would use them for certain calculations. So keep them in mind. All right, now we can start with the first part of this lecture, the particle density of the soil. Now, to understand the concept of soil particle density, I want you a little bit to pause and underline the term density. And try to remember from your background information, what is density? What is the equation of density? You would see that density is basically the mass over the volume of that things. So the soil particle density is exactly the same concept. You basically measure the mass of the particles, only the particles, and divide it over the volume of the particles. Now, to understand this and to imagine, look at the pictures. You would see that we know that the soil particles can be sand, silt, or clay. But we also know that in the soil, you always have the pore spaces and you have the organic matter. So to measure the particle density, you should exclude the other two things. You should exclude the pore spaces and you should exclude also the organic matter. And you only deal with the solid. Now, to conceptualize this and make it simple, let's imagine that you have a fixed volume. And this volume is basically a cube. Now, the volume, we can determine the volume of this cube by multiplying the area of one face times the 6 faces that you have, and that would give you the volume. Now, to calculate the particle density, then we have to assume that we will put all the particles, compress it in this shape to form this cube. And then it's without air, without organic matter, it's only the particles. And then you weigh it and you divide it by the volume of this cube, which is 1 cubic meter. And then you get the particle density. Now you would see that the unit of the particle density is basically can be expressed as megagram per meter cube, or it is the same as gram per centimeter cube, just conversion. And you would see that the particle density of the soil can vary between 2.6 to 2.75 gram per centimeter cube. Now, why this variation? And we only deal with the same thing, with soil. To understand this now, again, go back to the concept of cube. Now imagine you have this cube and it is only filled with quartz. And then imagine you have another cube which is only filled with gold. Now, which one of them would have a higher particle density? Think about it. It's of course the one which have a higher mass because our volume is fixed. Now, which one is heavier, quartz or gold? You know, especially the ladies, you know, the gold is very light. So basically the quartz are heavier. Now we can see that the difference between them is basically lie on the chemical properties of that particular mineral which form the particles. So if you have a mineral that is denser and heavier, then you would end up with a higher particle density compared to a lighter type of minerals like gold. That's why the particle density depends on the chemical properties of the mineral, but it is not influenced by the particle size. Regardless of the size, when you put them all together to form that particular volume, then it is the same value. And it is also not influenced by the arrangement of the solid particles. Why? Because now we are dealing only with the particles. All of this volume cube is 100% occupied with particles. There is no space, there is no organic matter, nothing. So it's incompressible. And that's why it is also not affected by the cultural practices like, for example, blowing the farms or adding vegetation or anything, because all of these effects will be excluded and you will only deal with the mass of the particles and the volume of the particles. Now, how can we quantify the particle density in the lab? Let's assume that I want to know the exact value of the particle density of the two examples that I use. For a particle made of quartz and another particle made of gold, they are all in the same shape, in the same size, everything is the same, except they are different in terms of the chemical properties. One is gold and the other one is quartz. Now, how to do it? Remember, the particle density is basically the mass of the particles divided by the volume of that particle. Now, the mass is easily determined. We can get a balance and we put the first particle, the quartz, we get the mass, then also we weigh the other particle, which is the quartz, and we get the mass. Now we get the mass of the gold, we get the mass of the quartz. But the volume, how to deal with it? Now, as you can see from the picture, the size or the shape of the particles might not be even, like in a regular shape. It is irregular in shape, so we cannot use mathematics to do that. So how can we determine the volume? Simple. You get a volumetric cylinder, you get a graduated cylinder, you fill it with water, and you can see now the level is just 30 ml. Now, once you put the first particle, which is the quartz, on the water, it will sink, and as it sinks down in the water, it will displace the water. So the level of water, as you see in the picture, changed from 30 to 35. And then you just subtract 35 minus 30, and that would be 5 ml. And then you just divide the mass of the quartz divided by the volume displaced, and that would be the particle density. Now, when you do the same process for the gold, the displacement, because the gold is lighter in weight, it will be less. That's why then the particle density of the gold will be less than the quartz. Now, what is the difference between particle density and bulk density? The difference is very easy. When we dealt with the particle density, we said that we ignored organic matter and the pore spaces. But in real life, in your soil, if you are dealing with the soil as a whole, pore spaces and organic matter always exist in the soil. Or maybe you might have less organic matter, but pore spaces is always there. And the pore spaces can be filled with air or water. Now, imagine the same thing, that we have cube, and this cube is made of soil. We can know the volume of this cube because we know that we can calculate the area and multiply it times the number of faces, and we get the volume, which is 1 cubic meter. But how to get the mass? Again, we weigh this cube, and we keep in mind that this time we don't have 100% particles, but we are dealing with the whole soil, including its organic matter and the pore spaces. That's why the mass will be much less, and that's why your bulk density will be much less. It's the same thing, mass over volume, but here we should include the pore spaces and the organic matter. That's why most of the soils, or the range of the bulk density of the dry soil, ranges from 0.6 to 1.6, but it can vary between one soil to another soil. Why? Because remember, each soil would have a different size of the particles, and different also, maybe different component that forming, or different minerals forming these particles. Now, as you just take a simple example and you compare pure sand particles, as you see in the picture, and pure clay particles. Now you have sandy soil and you have clay soil. Look at the sandy soil. The sandy soil, you have bigger size particles, and therefore you have bigger spaces between them. However, the mass of each particle is heavier compared to clay. Why? Because most of the sands consist of quartz, which is heavy. Now, when you go to the clay, you find it's only the particles are very small, and you have more spaces between them, and you have also less quartz on it. It's mostly other type of minerals. That's why it is lighter. That's why the bulk density of the sandy soil can be up to 1.5, whereas for clay it can be up to 1.2 something. So you see the differences between them now. And that's why, for example, when you look at the loam soil, it would have a bulk density from 1.1 to 1.4 because it has a combination of sand, silt, and clay, as you remember from the soil triangle. Now, even with these two things, even with the example of the loamy soil, you still find range 1.1 to 1.4. Why? It's the same, you're using particles. What can make the differences? Remember something, again, in your soil you have pore spaces, organic matter, water, and many other things. And all of these things can affect the bulk density. Now, arrangement of the structure of the particles itself. The arrangement itself can different. When you have it like this, if you just look at the sand particles example, when you have them like this, then you have a particular spaces between them. Then when you compact them and to make the same volume, then the mass increases. That's why it is affected by the arrangement of the structure. And it's also affected by the cultural practices. Now, if you, for example, plow the soil, you make more spaces on between the particles. If you add more organic matter, you are adding lighter materials to the soil. If you add more water, you are making it heavier. And that's why the bulk density can vary depending on the practices that you are doing. Let's take this final example to ensure that you got the idea of the difference between particle density and the bulk density. Now, imagine you have again a cube, and you are using the same cube to measure the bulk density and the particle density. And the cube has a certain surface area, you multiply it times the number of faces, this is times 6, and you got the volume, which is 1 centimeter cube. Now, again, for the particle density, you are measuring the mass over this volume. So the mass would be only considering the mass of the solids, only the solids, without the air, without the water, without the organic matter, only solid, 100% solid. You put them all together, compress them up to occupy entirely the full cube, and then you weigh them, and you got the mass 2.66 gram. Now, to get the particle density, divide just 2.66, the mass over the volume, and that would be 2.66 gram per centimeter cube. Now, use the same volume to measure the bulk density, and keep in mind that the bulk density includes the pore spaces and the organic matter. So when you put everything together, you got, let's say, 50% solid and 50% pore spaces, and the mass was 1.33 gram. So your density will be 1.33 gram divided by 1 centimeter cube, and that would be 1.33 gram per centimeter cube. Now, you see how the difference is? The only difference between them that when you deal with particle density, you are only dealing with the particles. When you deal with the bulk density, you are dealing with the soil as a whole. That's why the bulk density can be affected by compression, can be affected by the addition of organic matter, can be affected by anything that affect the pore spaces. Now, how you measure the bulk density in the field? Well, it's very simple. What you need to do is to get a well-known volume and then to measure the mass. So usually they use something called soil bulk density sampler, which is having something like you see and having a cylinder. Then you insert it into the soil, and then you know the volume, and then you weigh the mass and you get it. Now, to get this idea very clear, let's watch the following video in the next step.
In order to measure bulk density, the first step is to collect a soil core. This can be difficult in winter. After the core has been collected, remove a soil-filled ring from the core sampler and use a knife to flatten the edges. Weigh an empty soil tin and record its mass. Empty the ring of soil into the tin, making sure to get all of the soil from the edges of the ring. Place the tin in a 105-degree oven for 24 hours in order to dry the soil. After drying, weigh the tin and record the mass. In order to calculate the dry weight of the soil, take the weight of the tin filled with dry soil and subtract the empty weight of the tin. Record the soil weight in grams. Use a caliper or ruler to measure the inside diameter and the height of the ring. Use pi r squared to find the cross-sectional area of the ring and multiply that value by the height of the ring to get the soil volume. Record this volume in centimeters cubed. To calculate the bulk density, simply divide the dry mass of the soil by the volume of the soil.
Okay, after watching this example, I want you now to think. If you have two different soils, one soil is basically an area where you have it without vegetation, and the other soil you have basically the other area you have a soil with a lot of organic matter, you have also vegetation. Now, which one you might think have a higher bulk density? You're just using the same technique. Think about it for a while. All right, I think you would arrive to the conclusion that this soil which you take from the field with organic matter and vegetation would have higher or lower? Think. All right, would have a lower bulk density compared to the one with only with the bare soil. Why? Because you are using the same volume, you are using the same instrument, but then in the soil with organic matter, part of that volume of the cylinder will be occupied by the organic matter and by the roots. Those have a lighter mass and therefore more spaces, more pore spaces, and therefore they will have, at the end of the day, lower bulk density. They will lower the bulk density. Now, if you add water if you have now comparing two fields, the same soil, sandy soil, one is irrigated with water and another one is fully dry, which one would have a higher bulk density again? Of course, the one with irrigated. Why? Because you are adding even water to the pore spaces, and remember, the mass of air is neglected. So water mass is higher, and therefore you would have a higher bulk density. Now, let's see what is the relationship between bulk density and the pore spaces. What is going to happen? So to get the idea very clear, you have three different pictures. Look at the particles, how they are sorted and organized, and think which one of them might have a higher bulk density and how the pore spaces would affect the bulk density. Now, if you look at the first picture, you have particles which are rounded in shape, perfectly rounded, and they are sorted nicely like this. However, when you compress these particles, you compact them, work on them, compacted them, then the spaces between the particles will be a little bit like occupied, and by that you have to fill the same volume, and then you ended up with less pore spaces. And that would, what does it do with the bulk density? Now think about it. Now in the third case, you have a combination between the rounded particles and also with smaller particles. And in this case, you would see that the space even is more occupied. Why? Because the spaces between the larger particles are occupied and filled with the small particles. So in this case, that you have more particles in the third scenario. And these particles, let's assume that the big particles are sand particles, which you know are cords, and cores are heavy. And then even in the spaces there, you have another, like, let's say, fine sand. Now, what will happen to the bulk density? Basically, it's going to be increased. So we can see that the space and the bulk density are inversely related. The more the spaces you have in the soil, the less the bulk density will be, because these spaces would affect the mass. And remember, bulk density is mass over volume. Another important point that I want you to keep in mind, that different types of soil, of textural classes soil, would have a different values of bulk density. So if you compare a sandy soil with a clay soil, you would find that the sandy soil would have a higher bulk density, because sand are made of mostly like the quartz, and quartz are very heavy, you know them. And if you compare it to clay soil is mostly like smaller in particles, much smaller, and therefore you have more spaces, more pores there. And not only that, the type of minerals in the clay soil usually secondary types of minerals, and it's not quartz. That's why those are light minerals. That's why the mass of clay would be much lower than the mass of sand soil, and therefore you will end up with a lower bulk density for clay soil. Another thing that to keep in mind, that if you just compare the normal condition, if you compare sandy soil with the silt and clay, as you see in the mid picture here, and you compare the water movement between them, you would see that the clay soil have a lower water movement. That water like takes a lot of time to get into the soil because of the small pore spaces. Compare it to a sandy soil where just like once you put the water, it just like goes down. Now imagine that if you added compaction. Now which one is more compacted? Is it sandy soil or the clay soil? Of course the clay soil, as you remember from the previous lecture, its properties makes it very compactable, like it's more prone to compaction. And imagine that you increase the compaction, now you compacted these soils. It means that you further reduce the water movement into the soil. Something else to keep in mind, that the bulk density, although it tells us about the condition of the soil and the pore space in the soil, but it's not a good indication for the suitability of the soil for the plant. It's not the whole story. Why? If you look at the last picture, you would see that in a normal condition without compaction, the roots can go nicely into the soil comfortably and can go deeper to tap the water and the nutrient. In a compacted soil, the roots won't be easily penetrating the soil, and that makes it really hard for them and makes it suffering for them. However, this tells us about the condition of the pore spaces, but keep in mind that the plants need other things, like the nutrient, needs the water, needs the proper temperature, diversity of microorganisms, and so many other factors. That's why bulk density alone is not the whole story. You need other things to tell whether the soil is good for agriculture or not. After looking at the relationship between bulk density and pore spaces, we found that it is inversely proportional, that if the pores increase, the bulk density decreases. However, still a lot of you might ask themselves the question, that is really bulk density important for the pore space or porosity? Now I mentioned here porosity. What do we mean by porosity, and what is the difference between pore space and porosity? To get the idea of that, let's look at the picture here at the middle. Now, if you want to compare the pore space between sand, silt, and clay, what you can observe? We mean by the pore space the space between each particle to another. And you would see from this example that clay would have less pore space because the particles are small. But when we talk about porosity, we mean something else. We mean the total amount of pores exist in a particular volume of soil. The whole pores, we sum up all the pores. Or let's say the ratio of pore spaces to the solid. Now, if we use the same example, sand, silt, and clay, which one of them might you think that would have more porosity or higher total volume of, or higher volume of pores compared to the solid? Think about it for a moment. All right, you would see that when the particle size becomes smaller, the amount of pores in that soil will become more and more and more and more, and by this the porosity of that soil will become more and more. So clay soil have more porosity than the sandy soil. However, sand soil have more pore space, the space between each particle to another, larger space compared to the clay because of the size. So that's why porosity is also very important concept in the soil. And the porosity usually in the soil ranges between 30% to 60%. We express it in percentage. Why? Because the porosity only happens in the pore spaces. We are talking about the pore spaces. We're not talking about the solid. We're only talking about the pore spaces which can be occupied with water or with air. So if you have a soil that is more of clay, then you would have less volume of solid compared to the volume of pore spaces. Compared with a sandy soil, in a sandy soil you have larger particles, and that would make more volume or mass of solids compared to the volume of the pore spaces. Now, if you want to say that, is this information describes the arrangement or the distribution of the particles in the soil, like the previous example that we used when we said that you have compressed the soil and then you have small pore spaces between the particles? Actually, the porosity does not tell us that. Why? Because the porosity again just described for us how much volume of pores you have in this volume of the soil. So it doesn't tell us the arrangement. The arrangement, we have to look at the soil and look how the particles are arranged. Now, how can you calculate the porosity using equation? Very easy. The porosity can be indicated as F, so it can be expressed as we said, it's the volume of the pore space divided by the total volume of the soil. And you know that the volume of the pore space only include the volume of water and the volume of air, and the total volume is basically the summation of volume of solid, water, and air. Or you can use another equation, which actually is this one. So the porosity can be 1 minus dB, which is the bulk density, divided by dP, which is the particle density. Or you can use 1 minus Vs over Vt, and that would give you the porosity. So you can calculate the porosity by these three equations. But most of the time we would use this equation, which is the porosity is equal to 1 minus bulk density divided by particle density. But you have more options depending on the givings that you have in the question. And we usually can approximate the particle density to be constant, to be 2.65. So if you have any question with calculation and the particle density is not given in that question, then you should memorize this 2.65 gram per centimeter cube and use it to solve. After knowing more information about the relationship between porosity and the bulk density, you can also find more relationship between the pore space and the different types of textures. Now, if we just use these two examples, clay soil and sandy soil, I want to compare between them in terms of the pore space, the size of the pore space, the number of pore spaces, and the total amount of pore spaces between them, then you would find that clay soil have smaller pore spaces than the sand. I mean the space between each particle and another. It is smaller in the clay soil. If you look at the total number of pore spaces, you know that since clay are smaller in size, so you would have more pore spaces. As you can see from this picture, the total amount of pores in the clay soil are more than sand. And if you look at the total pore spaces, again you would find that clay have more amount of pore spaces than the sand. And something else to remember, that when we talk about clay, you remember from the structure of clay that clay itself can be like sheets, like the sheets of books. So you might have something called intra-aggregate and inter-aggregate, and this means that you have even more spaces in the clay because of its structure. To understand what I have meant by saying that clay have inter and intra-aggregate space, let's take the following example. Now, if you look at the left picture, you have a well-sorted sand. You see that you have particles of sand, and between these particles you have spaces. Now, to the right side you have clay aggregate, and you know what we mean by aggregates, meaning that you have particles and they are glued together to form a unit, to form a structure. So you are comparing a structure of clay with sand having the same thing. So when you look at this picture, you would see that clay aggregate have spaces, large spaces between each one and another. Actually, those spaces are called macro pores. And the macro porosity or the macro pores are usually the spaces which are larger than or almost larger or equal to 0.05 mm. Now, these macro pores are very important for many things. Why? Because they are the one where water and air can move, and they are the spaces where most of the roots and microorganisms and other animals can live. And they are basically between like the sand particles, or it can be between the beds. What we mean the beds by the aggregates, between the aggregates. Now let's look again at the clay aggregate example, and you would find that in this clay aggregate, inside it you have clay particles, and between each particle of clay to another there are also some pores exist, and this type of pores we call it internal porosity, whereas the spaces between each aggregate and another are the macro pores. So the micro porosity describe these spaces, in this case between each clay and another, and these spaces are very small. They are usually less than 0.05 millimeter, and they are referred as microporosity. Those are usually filled with water, but they are too much slow. They are too small to allow water and air to pass through them, and even the roots, and even for the microorganisms. And if water is there, it will be tightly held, so plants cannot use it and cannot abstract it. But the most important thing for us to remember here, that which one is more important? Is it the pore space or the total amount of pore space? Now, I'm not confusing you, but which one is more important, pore space or the porosity, when it comes to water movement, aeration, and so on and so on? Think about it, and you would find that the pore spaces are more important. Why? Because the pore spaces are the one where water, air, and everything pass. And let's say that in a soil, if we know that the pore space in this soil is large, this information would be more beneficial for us to tell us how easy the water and roots and other organisms will live and pass there, compared to know the porosity of that soil, because the porosity does not describe how like the spaces between these. It tells us only the general picture, the total amount of pores in that particular soil. That's why pore space are even more important for us. To show you another example, links the porosity and the structure, the microporosity and the macroporosity. Look again here, that if you have the coarse minerals, particles, and aggregate, and an aggregate, you would find that the sand particles are large enough and their size is almost of the same size or the size of the clay aggregate. And you would find that in the sand minerals or the sand particles, you don't have microporosity, you only have macropores, the spaces between the particles. In the clay aggregate, you would find that inside the aggregate you have small particles, and between them you have the microporosity, and between each aggregate and another you have the spaces, and this is called the macropores. And in this example, we would see how the pore space can affect the microorganisms and the water and many other things. So again, if you have larger pore space, it means you have more space for water, for air, for easy movements of roots, easy movement of water and aeration, and so on and so on. However, if you have a smaller pore spaces, then it means that water would be hard to move, and the movement of water, animals, roots, everything would find it difficult, because most of these spaces are occupied with other minerals or other particles, no spaces, and then you would have also a limitation in water, limitation in nutrient, and so on and so on. And this can be affected a lot by compaction. When you compact the soil, as you see from the picture here, you are actually reducing the pore spaces, and therefore you would create all of these problems. Now let's take a little break and refresh our mind with some very nice exercises about bulk density, porosity, and other things. Now what I want you to do in this example is to calculate the bulk density and the porosity. Now assume that you took the soil bulk density sampler and you went to the field, and then you put it into the soil, and you got your soil. And as you can see that you have a cylinder, and you sample the soil with this cylinder. So the cylinder have a known volume. You know that it has a diameter of 4 centimeter and a length of 10 centimeter. And then after you weigh the soil before drying, you had the mass of the container that you used was 5 grams, and then you have the mass of the soil with the container 251 grams. And then after drying it, as you saw in the video, you have to dry the soil to get the bulk density. You got the mass of the dry soil and the container 169 grams. So how would you calculate the bulk density, and how would you calculate the porosity? To do that, the first step is to go back to the equation. What is bulk density? Bulk density is the mass of soil divided by the volume. And in this case, we want to calculate the dry bulk density, dry mass bulk density. So we have to use the mass of the dry soil only. But what is the volume in this case? The volume is easily determined, can be easily determined, because we know that we use the cylinder, and we know that the volume of a cylinder is equal to pi r square L. And therefore, your bulk density will be mass of soil divided by pi r square L. You put everything together, and let's start with calculating the dry mass. So the dry mass would be the dry soil plus container minus the weight or the mass of the container, because we only need to deal with the soil, not with the container, and that would be 164. And then you calculate the volume, you put everything together, and then you get the volume 125.7 centimeter cube. Pay attention to the units. The mass was given in gram, and the volume and the length things was given in centimeter. And then you just calculate the bulk density, mass over volume, and that would be 1.3 gram per centimeter cube. Now let's calculate the porosity. You know that one of the equations for porosity is 1 minus bulk density divided by particle density times 100. So now you already have the bulk density because you have calculated it. but we don't know the particle density. But remember from the beginning, I told you that you should remember something, that the particle density, if it is not given, then you use 2.65 gram per centimeter cube. So we apply everything in the equation, and it will be basically like this. If you put everything, you put the bulk density from what we have calculated before, and then you put over the particle density, you apply everything, and you calculate, and you get it in percentage, 50-51. Now the second exercise is also very interesting, and in this exercise you have taken a soil sample, and this sample weighs 0.7 kilogram, and the volume is given this time, 3.5 times 10 into minus 4 meter cube. Pay attention to the unit. And after drying, the mass of soil, or the weight, was reduced to 0.6 kilogram. And you have given also the particle specific gravity, give you 2.6 gram per centimeter, or per centimeter cube. And I want you to calculate the moisture content in the soil, the dry bulk density, the wet bulk density, and porosity. So spend some time, analyze the question, and use the equation and calculate it. Now the first and easiest part to do is to put the givings aside. So what the question gave you the mass of the soil before drying, 0.7 kilogram, and it gives you the dry mass, 0.6 kilogram, and it gives you the volume, which is 3.5 times 10 into minus 4 meter cube. And give you also the specific gravity test, which basically give you the value of the particle density. So the particle density in this example is given. Now, how do you calculate the moisture content? Very easy. You use the following equation. A moisture content is basically the mass of the moist soil minus the dry soil over the dry soil. You put everything and you get it easily, 16.7%. Now to calculate the dry bulk density, you just need the dry mass over the volume of the soil, and it is given. So it's very easy. You just put 0.6 divided by 3.5 times 10 into minus 4, and that would give you this value. Keep in mind that if you need any unit conversion or anything, just pay attention to that part. So in this case, you don't have to convert the unit, and the value of bulk density will be reported in kilogram per meter cube. So that's fine. You can report it as gram per centimeter cube or kilogram per meter cube. Now in the next step, I want you to calculate the wet bulk density. And in this case, you have to use the mass of the soil before drying, or the moist soil. So you use 0.7 divided by the volume of soil, and you will get 2000 kilogram per meter cube. In the last part, you have to calculate the porosity. So you have the equation, you know the porosity, that equal to 1 minus the dry bulk density over the particle density times 100. But look at the units. Do you have to convert anything? Do you have to do anything here? Well, the unit of the bulk density is in kilogram per meter cube, and the unit of the particle density is in gram per centimeter cube. So we have to convert the unit of the particle density. So how to do that? Very easy. Now you know that 1 meter have 100 centimeter. So 1 meter cube, you just use the cube for the meter and use the cube for the 100, and then you can get the relationship easily. You don't have to memorize things, just use your basics and your understanding. So then you will get that 1 meter cube would have million centimeter cube. And then you just put 2.6 and you put the unit, you cancel the unit. As you can see in this example, the gram or 1 gram or 1000 gram in 1 gram in 1 kilogram, and then you know that 1 meter cube have million centimeter cube, and then you cancel everything, and then you get the particle density as 2600 kilogram per meter cube. Now you don't have any problem with the unit, you can just use them direct 1 minus the bulk density divided the particle density times 100, and that would give you 34.1%. Now let's look at another very important concept. Are there any factors that affect the porosity of the soil, and what are they, and how they affect the porosity? Now, one of the factors is the soil texture, and we have seen that different type of texture or different type of soil texture would have different mineral content and different arrangement. So usually if you have sandy soil, you have about 35 to 50% pore spaces. Compared to finer texture, you have smaller particles and therefore you have more porosity on it. So you have from 40 to 60%. Now, aggregation is another example that you know, because once you have more aggregates, you know that the aggregates would have more spaces or larger spaces between them. Depth of soil. Now, something very important, that if you dig a pit, okay, and you try to measure the bulk density and the porosity using these equations, then you would see that if you go down, the soil gets more compacted. And not only that, if you go down, you are far away from the organic matter, far away from the roots, far away from all these factors. And therefore, going down would increase the bulk density, and therefore you would reduce the porosity. So going down, you have less porosity compared to the top soil. Vegetation also is another factor. If you have a soil that is cultivated, then it means that you have roots, you have organic matter, and if you have roots on organic matter, this creates more spaces, and therefore basically you increase the porosity. Compare this to uncropped soil or bare soil without vegetation, then you are eliminating the organic matters, you are eliminating the roots effects, and you are eliminating the other things, and therefore you will have higher bulk density and therefore lower porosity in that soil. And finally, we have approached the last part of this lecture, which is a comparison between the physical properties of three different types of soil. So if we have sand, loam, and clay soil, as you look at them in the triangle, look at where these soils exist. So clay at the top of the triangle, then you have loam at the center almost, and then you have sand at the bottom left corner of the triangle. Now, what are the differences between them? If you look at the particle density, it's the same for all these three soils, because particle density deals only with the particles. However, when you look at the bulk density varies. So sand have a higher bulk density compared to loam and clay would have the lowest one, because in the sandy soil you have quartz, it's made of quartz, the particles are large, you have less pores, you have less porosity, and therefore you would have a higher bulk density. Now, if you look at the porosity, again, the porosity, since you have higher bulk density in sand, definitely you would have a lower porosity compared to clay. So clay have a lower bulk density, but it has a higher porosity. And if you look at the pore sizes, the pore spaces between sand particles are larger compared to loam, and clay have the smallest size. However, when you look at how these things affect the water movement, you would find the permeability, which describes the water movement in the soil. You would find that since the particle or the spaces or the pore space between the particles in sand are larger than other types of soil, therefore water moves easily in the sandy soil compared to clay and loam. Now, which one of these soils would retain more water, would hold more water, is basically the one which have more pore spaces, so, or more porosity, I mean. So since in sandy soil the water will move easily, once you put it on the surface it would drain easily, it actually retain less water. That's why the water retention in the sandy soil is less. compared to clay. Clay, yes, the movement of water would be very slow, but since you have more porosity, then you can hold that water into the soil. But again, remember these things, the porosity and even the bulk density, they cannot tell the whole story about the suitability of this soil. Keep in mind that you still need to consider the nutrient and many other factors. And keep also in your mind that yes, clay hold more water, but can the plant absorb all of this water? Remember that clay have more micro porosity, which means in the micro porosity the water is held tightly and the plant cannot use it. So loam soil would be the best soil for agriculture in terms of holding nutrient, in terms of easy movement of water, aeration and roots, and many other factors. So that's all for this lecture. I hope you enjoyed it. I hope you learned a lot of things about the physical properties of the soil and you discovered new things about it. So stay safe and see you. Bye.